your size, in your opinion?
A little bit of both. So there is some chemistry that is required as far as an understanding of some of the biological processes that go on within the body, as well as some of the aspects of being able to classify and interpret arterial blood gas, looking at fluid and electrolytes, a little bit on nutrition. There's chemistry that comes up in pharmacology, so a little bit of background you need to have for it. When we talk about matter, we talk about really anything that takes up space, has a mass, and can be perceived. So if it's something, it's matter. If it's nothing, it's not matter. And there's three primary states of matter that we'll talk about: solid, liquid, and gas. They ask, what about heat? Well, heat's not really matter. It's a manifestation that happens. We can divide matter into two different groups: pure substances, which are homogeneous in nature. No matter where you find them, they're the same. And examples of that are elements and compounds. We can have a mixture, which can be homogeneous or it can be heterogeneous. And those are examples of solution suspensions and colloids. And we'll talk more about those later on. What about the pure substances? The matter in its simplest form, from the most basic atom up through a combination of atoms making an element, two or more elements together making a molecule, and then a bigger size of molecules put together are compounds. So there's this building block that goes on there. And because they're pure substances, they're the same no matter where they're found. Oxygen is oxygen is oxygen. Water is always the same. Okay? You can't break it down any further without a chemical or nuclear reaction, in which case it would become a different substance. Think about uranium that's in a nuclear fission bomb. And as I mentioned, they're homogeneous in the sense that they're uniform in structure. No matter where you look at it, it's still going to be the same exact thing. So what about an element and compound? Well, an element is, again, a pure form of matter that are there. And they're basically large collection of atoms of the same type. They can't be broken down further and still maintain its identity. And all elements have the same atomic number. No, that's not how I really want to say that. I just realized that. Oxygen as an element will always have the same atomic number. Or a better way. It's not that all elements have the same atomic number, because we know that they all are different. They're not bonded, but they exist together. Not necessarily bonded. The listing of all the elements that we know of is called the periodic table, and like I said, we'll have a couple of lectures talking about how that table is set up and why it's periodic. But you'll see different numbers as far as how many elements there are. I would never ask you how many elements are there, but somewhere around 117. And if you look at a periodic table, you'll see the atomic number listed on top, the element's name, its symbol, and its mass as far as what 1 mole of it would weigh as a unit. And we'll talk more about what those things are in a bit. Okay, 118, whatever. They keep discovering new ones. If you look at a periodic table, you'll notice there's some spots where they have holes in them because they know that there's an element that fits that spot. They just haven't been able to find it yet. 91% of all the atoms in the universe are hydrogen, 9% are helium. So the most abundant element in the universe is hydrogen. With helium coming in a second. Other elements are only there in trace amounts. If you add 91 and 9, you get 100, so there's got to be some rounding that goes on there, but very, very narrow. When we talk about the Earth, on the other hand, oxygen is the most abundant element that we end up having. And you look and you see hydrogen down the list, and helium's not even on the list. but there are some other ones that are there within the Earth, oxygen and silicon being the two major ones that you end up finding. So these are the major elements that I want you to be aware of as far as what is in the human body. And the body, again, is made up, about 2/3 of the body is made up of water. And then we can subdivide the remaining elements into some that are macronutrients and some that are micronutrients. I would like you to know the macronutrients: calcium, chlorine, potassium, phosphorus, magnesium, sulfur, and sodium. The micronutrients we don't really worry as much about, but they are necessary for some protein construction and some other bodily functions. One of the problems that we kind of realized later rather than earlier was when we had a patient who could not feed themselves in the ICU. We would give them, they would have an IV bag of dextrose and water. Well, 5% sugar is not a whole lot of nutrients that you end up having. So they created what they called total parenteral nutrition, or basically they would just put into a large IV a solution not only of the major elements in the forms of proteins, fats, carbohydrates, but they would also include the macro and the micronutrients. You and I get selenium, for instance, no big deal. It's in some of the foods that we eat quite commonly. But if you're not eating, you're not getting that item. And when you get to things like iron and copper and manganese, those are very important for muscle building and, like I said, for protein construction. So we ended up including those trace elements in the solution, which was kind of a oops. Should have thought about that one before. So those are elements. The smallest particle of an element are atoms. And again, they're pure substances. They can be combined of similar atoms in the case of oxygen, or of different atoms, as in the case of water, where I have two different elements, hydrogen and oxygen, blended together. A compound is a collection of molecules. Okay, so these were molecules that we're talking about. Oxygen molecule is O2. And then a compound is basically a collection of molecules together that can be broken down into smaller components, molecules, and elements. So here we have the most basic elements. They're made up of atoms, and then these atoms and elements can mix together so that we end up having molecules where they're bonded together, or compounds where each of these individual molecules are bonded together. You get the gist of how this building block goes. Starting off with atoms, elements, molecules, compounds. Again, the smallest particle of that element is an atom. And why I have that on there, I don't know. Head of a pin could hold 100 trillion atoms, whatever. They're very small. The atom itself can be broken down to three primary particles that I want you to know: the electrons, the protons, and the neutrons. Technically, they can be broken down further. The protons and neutrons are made of subatomic particles, positrons, mesons, and neutrinos, but who cares? Let's not go there. Okay? We're good enough with protons, neutrons, and electrons. Helium atom has protons, neutrons, and electrons. The protons and neutrons are in the nucleus in the center, and the electrons are floating around in a cloud or an orbit, if you will, around the nucleus. So the protons are positively charged, neutrons are neutrally charged, electrons are negatively charged. So in this case of the helium atom, I have two protons, two neutrons internally, and then I have two electrons in a cloud around that. because the protons and the neutrons are in the center, they're basically the nucleus itself is positively charged. The electrons that are in this cloud or shell that go around it are negatively charged. We call the things that are inside the nucleus nucleons. And when you look at it, the size of the atom is very, very small. And the nucleus, you know, as far as the size, it doesn't count. But what it does constitute is the mass. Because neutrons and protons have a larger mass than electrons, as we'll see, most of the mass of the atom is on the inside. So again, small atomic particle, protons. Whenever we look at the atomic number of a substance, that's how many protons are present within that nucleus. And the charge of an atom is always neutral. So if I have 4 protons, I have to have 4 electrons to balance it, to make it equal. Neutrons, on the other hand, differ. Neutrons, even within a substance element like oxygen, you can have multiple variations of that, where the number of protons are always the same, but the number of neutrons differ. When the number of neutrons differ, we call this an isotope. And an example of that would be oxygen that we breathe versus ozone, O3, which isn't oxygen in the same form, has a different number of neutrons. So you can have a situation where they have the same atomic number, meaning the same number of protons, but they have different number of neutrons. Because neutrons have mass, then the atomic mass of that element will be different for each of the isotopes. Does that make sense? What makes up the mass of an electron, or mass of an atom, are protons and neutrons. So if I have the same number of protons, but differing number of neutrons, the overall mass of that atom is going to be different for each of the different isotopes. Finally, electrons, where protons and neutrons determine mass, electrons determine size. Okay, so when we're talking about distance, these electrons travel in a huge cloud around the nucleus, and that cloud is negatively charged. The mass of an electron is extremely small, so it doesn't really contribute to the overall mass of the atom, just the size. Okay. Nucleus determines mass, electrons determine size, and I use the example, if the electron cloud was the size of Ford Field, the nucleus would be smaller than a pea at the center. So it's a huge amount of distance that we're talking about, comparatively. Electrons determine size. Nucleus, which means protons and neutrons, determine mass. You think I've driven that point home enough? You may see that at some point along the line. By the way, our test on we got test Tuesday, Monday and Tuesday, I think it is. No, but this material will not be on it. Just math. Mm-hmm. The stuff that we didn't cover. And the stuff from before. But you will be able to use a calculator. Yes? Rearranging, a lot of conversions. Not that much from the probability of the statistics. I didn't put it on this test. So you'll see it next time. Sure. Sure. The other thing that electrons are important for is that the electron is what causes chemical reactions to happen. So the number and the arrangement of the electrons determine the chemical properties of the element. How many electrons it has specifically in its outermost shell will dictate how it will interact with other elements. So sodium chloride, it's the outermost electrons that actually join together to form the compound salt. Okay? So chemical properties, electrons. Okay. So here's our periodic table where we have the element name, the atomic number. So hydrogen, how many protons does hydrogen have? How many electrons? How many neutrons? None. We'll find out that the mass of a proton is 1, the mass of a neutron is 1, the mass of an electron is negligible. So because the atomic mass is 1, that means it's only got 1 proton and no neutrons. More on that later. Okay. Number of protons is told by the atomic number. Given that the protons and electrons are equal, they have to have the same number of electrons. So if I said boron was atomic number 5, how many protons? How many electrons? Boy, that was easy. There's this thing that we use, it's a convention, it's called an atomic mass unit, and this is really how we express the mass of these substances. And it reflects the mass of an element that we report on the periodic table is the most frequently found form. So the mass of oxygen is 16, I'm sorry, I said that wrong. Yeah, 16. So that means that there's, it's the most common form as opposed to including ozone in there or something. But if you want to be technical, you can convert atomic mass to grams by looking at this very, very small mass of, very small expression of mass in the form of grams. Hydrogen, it's an extremely small number, and we express it as this AMU unit just to make life easier. I don't know why I have this line. 12 eggs. An example is the word dozen. Dozen eggs means that there's 12 eggs in the bin, but it doesn't say what the size of the eggs are. So where the quantity is expressed, the mass is not. When we talk about what makes up mass, as I just said, proton has 1 atomic mass unit, neutron has 1 atomic mass unit, and electrons have negligible. So we just ignore them. So carbon has kind of become the comparative element to everything else. Its atomic mass is 12. So we know that if it has an atomic mass of 12, it's also an atomic number of 6. So it has to have 6 protons, 6 electrons. And that atomic mass of 12 tells me there has to be 6 neutrons. If I take the atomic mass, subtract off the number of protons, whatever's left yields the number of neutrons. And we kind of just round that 12.011 atomic mass units to 12, because it's just out of convenience. Hydrogen, on the other hand, has about a 1/12 of the mass of carbon at 1 AMU. So as I said, it has 1 proton, 1 electron, and no neutrons. Magnesium is twice the size of carbon. Atomic mass unit of 12. Atomic mass unit of 24. Atomic number of 12. So there's got to be 12 neutrons. These isotopes we talk about, again, are different forms of the atom with the same element. And what is happening is the number of neutrons vary. Neutrons will determine physical properties. So where the chemical properties are dictated by the electrons, Neutrons determine the physical property. What do we mean by physical property? Well, how they appear. Is it a liquid at room temperature? Does it have a specific color? What is its boiling point? Those are all examples of physical properties that vary based upon the number of neutrons you have. And virtually all the elements have isotopes that are present. From a chemical reaction standpoint, they should act the same because the number of electrons don't change, but what does change is the appearance of them that you would end up seeing. A couple of areas where we use isotopes. One is a radioactive form of xenon. Gotta love xenon. Anything that begins with X, you just gotta love. And we use that in nuclear medicine, things like bone scans and the ventilation and perfusion scans, where in the form of a typical radiographic film, chest X-ray, we're shooting a radiation beam through your body and picking it up on a plate on the opposite side. When we're doing nuclear medicine, on the other hand, we're injecting you with a nuclear material, and you emit it. And depending upon, in the case of a ventilation perfusion scan, we use xenon as the trace gas. We have you breathe it in, and then we can see where it ends up going into the body, both from a ventilation standpoint as far as you breathing in and injecting it into the bloodstream. Okay. And we compare the ventilation to the perfusion. But that's isotopes. So same number of protons, same number of electrons, different number of neutrons. I think I said everything there. The only difference is the mass. The mass would change for each of the isotopes because the number of neutrons change. Here's an example of an isotope, chlorine. Chlorine is atomic number 17. Has an atomic mass of 35.45. This is one that's kind of unique in that 76% of the time it appears as chloride 35, which is why we use the atomic mass number of 35. 24% of the time it shows up as chloride 37. So because the most common form is that chloride 35, what they actually did is they went and determined what percent of it is made up of this, and they multiplied the percent times the mass, added them together, and this is the only oddball on the periodic table that's kind of in the middle. So where most of the elements are very, very close to a whole number, chlorine's kind of on its by itself. So I try to stay away from using it in calculations because of that. So again, most common type of 30 is the 35. We know that from a 17 atomic number, they have to have 17 protons, so that means 18 neutrons are present in the most common form. So take the atomic mass, subtract off the atomic number, and that's the number of neutrons that you have in the most common form. And we know that most of the mass of the atom is made up from the protons and neutrons added together. So here's our example again. If I would feel comfortable giving you an atomic mass, not chlorine necessarily, but giving you what the mass number is, giving you what the atomic number is, and you determining how many neutrons are present. It's just mass number minus atomic number. Potassium, better example. Atomic number 19 means how many protons? How many electrons? How many neutrons? Well, it depends. Am I talking about the mass number 39 or mass number 40? In one case, it would be 20. In the other case, it would be 21. So it depends which one we're talking about, which of the isotopes we're talking about. And here's an example, atomic number 8 for oxygen, 8 protons. If the mass number is 14, that means there's got to be 6, 7, or 8, and 8 electrons. The number of electrons are the same for each of the isotopes. What doesn't change is the number of protons and number of electrons. Just the number of neutrons. That was painful. I like this one. Okay. So again, there's